I just want to talk to you about two specific projects that worked on looking at privacy in communication, trying to apply ideas from both differential privacy and this measure called maximum leakage in two different contexts. So to sort of set the stage, the thing that I think is very interesting and different about, I've worked a lot on differential privacy in the context of just learning a single machine learning model. But here, what I'm trying to think about is that we have a bunch of devices which are trying to measure a system state, and the legitimate receivers are interested only in some aspect of the state. So I don't actually need, for example, if you think about smart home metering, you don't actually need to know the load on the circuit at a millisecond resolution. That's not what the legitimate user necessarily needs to know. And so but a non-legitimate user might want to actually estimate the state, or might want to estimate events that are happening in the network. So that's the kind of question that we're looking at. So when we kind of started looking at this problem, this is work that I did with Narayan and student CJ who's graduated. So we looked at data from a couple of different, common home IoT type sensors, and just looked at this group at Princeton, which kind of measured the traffic that came out of these devices just to see what it looks like. And you can see that the traffic characteristics are not maybe like the same as you would expect out of streaming video, like we were just or streaming VR, like we were just seeing before, right? And in general, if you think about these type of systems, they're like, again, the different timescales to think about. So one is this real-time application I talked about earlier this afternoon. But the other is just like these kind of sensors are interested in detecting events, which happen at a kind of slow time scale. You fall asleep, it sends a text that you fell asleep, it sends some packets. That doesn't, well, maybe if you're me, you fall asleep and wake up many times in short succession, but generally speaking, not so much. And then, and also in many of these applications, you're gathering data for offline processing. So that's maybe more, again, for kind of traditional differential privacy. So I think one thing to think about is that there are many different opportunities through which you could intervene and talk about guaranteeing privacy, whatever that means. And a lot of times when you talk about these sorts of things, they talk about something called a privacy barrier. Whereas at this point, after this link, we've guaranteed privacy, and then we can sort of in differential privacy, the hope is that once you say, okay, I'm going to make this link privacy preserving, then I don't have to worry about what happens later on. That is, there's this post-processing invariance in differential privacy, which says that I can make the guarantee at a certain point, and any post-processing is not going to degrade my privacy guarantee. So you could do this at the sensor. So you could manipulate your actual measurements. And Jorge and I have actually talked a bit about doing this in the context of smart buildings. And you've actually done some experiments on noising up sensor measurements. You could also do this at a gateway, for example, in a smart home, in a home setting. You have a bunch of different devices that are connected to a network gateway in your house, and that gateway could try to do something to manipulate traffic, manipulate the measurements that are coming out. And the third one is at the server, where you get to control, say, somebody's API access to the data, which is another thing Jorge and I've talked about. I've worked on in the context of other projects where that's kind of the setting where often differential privacy feels like most at home, where you say, okay, I'm only going to allow you certain queries. And I know how to make those. I know how to protect. You can query the data, and I can protect the answers to those queries. So actually, one thing I want to I guess I'll bring it up in other contexts. So the first project I want to talk about is looking at traffic shaping, and this is the project with Narayan and CG and the NSF project that just wrapped up. So when we think about privacy, people often sort of think of privacy and security interchangeably. You see this a lot when people talk about privacy and security, or security and privacy. And so, but it really is important to think about the difference. So there's sort of encryption, which is standard and can be used to protect the payload of a packet, the actual data that's being transmitted, and that's very effective. And I think and so in some sense, that's not the thing we're worried about here. We're worried about these side channels, which are the timing and packet sizes that can reveal a lot of information about what's happening in the network. So we look at see these two sensors. The traffic is, as I said, very intermittent, very bursty. Also, the packet sizes distributions are very different for different devices. So I can tell just by looking at the packet sizes not only what device is transmitting, but like what is happening in the home, just from looking at the timing and packet sizes. So people have looked at this before. This is not a novel finding, not my finding either. And also, if your interactions with your mobile, with the smart home mobile apps, also generate distinguishable packet sizes and sequences. So two concrete examples are, I think, in this figure, there's a I think it's the green one, the little green, first sort of medium-sized little green taller packet. That packet at 7 seconds meant that the Nest camera actually detected somebody moving in the frame. This other packet at 30 seconds, this big one, meant that the Sense Sleep monitor detected that you fell asleep and then sent a packet saying, "Oh, your person is asleep now." Right, and these are very distinctive sizes, and then the timing will reveal actually when the event happens. And so that's why I ask you to sort of compare and contrast to problems that well-known problems that we see when people talk about smart metering for power networks. So a lot of work on network traffic privacy focuses on anonymity and looking at anonymity of source destination pairs. So you want the router to do some packet mixing, or somehow obfuscate the source destination. Privacy there gets quantified using entropy or some other information theoretic quantity. And one of the standard techniques there is to do mixes, which were introduced by Chom in a very forward-looking paper in 1981. It's like one of these. I don't know, because I say that because I was born in 1980, so I couldn't look at, I wasn't even looking at anything in 1981. But it was, and then there's other things you can do, which we'll still get, is you could introduce dummy traffic, and this introduces more overhead because you're sending more packets, but they're garbage packets, but that helps protect identity of what's going on in the network. So what we're doing is we're kind of looking at these ideas that have been sort of proposed before, but looking at the context of what sort of privacy does it provide in differential privacy context. So we're looking at a sort of discrete time to set up them. I'm not setting up the formal model here, but we're using a discrete time model. And the central thing that we're trying to understand is what happens if a traffic shaper can actually do surgery on the packet. So I can queue up packets, I can cut them up, I can reassemble them, I can pad them out, I can do a bunch of different things to to that. And then we're going to use differential privacy to measure what is lost in this system. You can delay them. Huh? You can delay them. You can queue them. And that's going to introduce. So what is the cost? The cost is extra. You're sending, if you pad things out or you send extra dummy stuff, then you're wasting network resources. And if you're queuing or something like that, you're increasing delay. But if we think about these kind of applications, I mean, does it matter if I delay the sleep onset time by like a minute even? Probably not. Right? It's probably not a big deal for this type of application. So you have to, I think the thing that maybe we didn't appreciate when we first started thinking about this project is the heterogeneity of these devices and the kinds of traffic that they generate, and that maybe it's impossible to provide privacy for some things, but maybe it's easier to hide this kind of intermittent stuff if you also have a lot of background traffic. You can hide it in the background traffic. There are also devices which poll at very regular intervals. Yeah, so that's another type of thing that you can see. So we're interested in trying to protect the type and timing of an event. That's the sort of what we what we're trying to understand in terms of the privacy. So one question would be, for example, did this switch turn on and send this large packet at time slot S or not? That's the kind of thing we'd like to say. We'd like to make it hard to determine if that was true. But we also wanted to know about like types of things. So for a particular sensor, is it just checking the camera feed, or is it actually detecting a motion, or the timing of event? Did you fall asleep at 10 versus 11? That might make a significant difference in terms of your sleep quality. Like I said, we can do this shaping in surgery. So the idea is that we want to quantify how much does the output packet stream, the timing and sizes of that output packet stream, reveal about the input packet stream. And what can we do? And we're allowing ourselves to do these kind of operations. And the cost is going to be extra delay and overhead in terms of the number of bits. And that's a quick question. Yeah.
Where is the shaping taking place? Or what do you?
We're thinking about it as happening at a gateway that's sort of between, like, sitting in your house before it goes out to the wider network. Yeah. Something happened to my figure. Okay. So it's like half of it's missing. We're using differential privacy. It's privacy preserving, right? I gave a talk once on jamming, because that was what I worked on for my thesis, was jamming, and the projector went out. So I was like, exactly, adversarial communication is happening right now in front of you. We're trying to use differential privacy to measure the information leaked. So we're going to try to use this epsilon delta differential privacy, or epsilon differential privacy. And the one thing I want to point out is that this is privacy for events. It's not where you typically, when you think about differential privacy, people are talking about, I have records measured for individuals. So I have the data points from each of you, and then I want to train a classifier that's going to be able to tell, whether or not, I don't know, estimate the regression model to estimate your height or something like that based on some other measurements. And here, this is not individual level. We're not talking about individual identifiability kind of questions. We're actually just asking whether an event happened or not. So this is, I think it seems very obvious when you say it. So maybe it doesn't seem, I'm not saying it's deep, but like it is different than if you try and like pick up tools from differential privacy and try to interpret what's happening, it's not the same. But what differential privacy does, if you're not familiar with it, is it uses randomization. It's going to randomize the output in order to mask what's happening, what's at the input. So we can look at, so we tried to do a sort of systematic study of the different types of shaping mechanisms. And, one thing you could do, for example, is you could just uniformize the output. You could just, whatever you had, just send a packet every, slot or every other slot, and the same size. And as long as they're big enough, you'll be able to send whatever valid thing is, and you can send dummy pack bits for the rest of it, and it'd be fine. And so we can basically ask if the size of the packets is going to be constant. So if the packets are the same size every time, or if the timing is going to be regular or variable. So you can look at these different, different classes of policies in this way. And, if you, for example, if you do make if you make the output traffic look independent of the input traffic, then clearly you've protected all sorts of, you've got a perfect privacy, but maybe you've, wasted a lot in terms of overhead. So that's the question is, can differential privacy help us manage this trade-off, manage the trade-off by saying, I'll give up a little bit on privacy in order to protect against timing, the timing and type of an event. So, we did some experiments. These are not the real network experiments. We did some real network experiments on orbit, which I didn't put in the figures here, with a paper that Mohsen has not bothered us about, but we should probably work on that draft. Where we implemented this method on in orbit. But here is like, you can see if you make all the packets the same size, then you got perfect privacy. You can also look at situations where you pick a random packet size every time, but you still send something. You send something every time slot, but you pick a random packet size every time, and maybe this will help you manage burstiness. But the big thing I want to point out in this, which is kind of the main thing to think about, here is that, all of the models that all the mechanisms that we think about trying to optimize so far, and that are easiest to think about in terms of optimization, kind of assume an IID input packet stream, which is totally bonkers because that's not actually what the traffic looks like. And things will behave quite differently. I mean, the outputs will look quite different if your traffic is bursty. So for example, this thing on the top side where you have IID input traffic, the output traffic, it doesn't seem like, it seems like it looks pretty uninformative regarding, for example, that big spike there. But for example, this burst that happens in the lower thing is maybe less. It's going to be less apparent if you spend a lot in order to if you guarantee a lot of privacy here, you can see that it actually in fact does mask that burst. Whereas if you try to use differential privacy, it will be if it's agnostic to the memory, it doesn't take into account the memory in the system, you're going to be able to see things. So this is where you can sort of see where the leakage is happening. The main finding really is that the perfectly uniformizing the output traffic is very costly. So it might be you can use differential privacy to let you trade off the delay and overhead, but but the price is that you're going to reveal something about the traffic, maybe not the particular event of a particular large packet happened at a certain time, but you will still reveal something. That a lot of stuff was happening, for example, over at the end there. So the second project I want to talk about is a project also with Narayan and Roy and our student Nitya, who is not here. I guess not here. Okay. She should really get the talk. But so here, I was going to get her to come up here and do it. But we're looking at a slightly different model here. It looks like the same model, but we're using different mechanisms here. So we're going to focus only on thinking about protecting event timing, and we're also looking at what does the output Y reveal about the input traffic X. But here we're just going to think about timing. But now we have a constraint that the entity receiving on the other end has a latency constraint, which might not be true in some of the examples that I gave for the example sensors I gave before, but in other applications will be quite salient. And so what's the question is, if I send you information about what's happening in the system in a timely way, then you're going to be sure you'll be able to have a good estimate of the system state, but maybe you'll be leaking information about when the system state changes or events that happen there. So again, we're interested in understanding what does Y reveal about X, and in terms of like what is the mechanism that generates your output Y? What's kind of you doing queuing or something else? And here we're going to look particularly at this privacy metric. Instead of differential privacy, we're going to think about maximal leakage. And maximal leakage, I mentioned earlier in the afternoon, is as an information theoretic model. I'll give a formula in a second. But one of the motivations is exactly this idea of keystroke, like looking at keystroke timing. So just the timing between, if I can tell the timing between keystrokes, I can then infer which keys you pressed on a keyboard. And it's trying to control that kind of inference. So are you able really to reconstruct the actual keystrokes? And so what you can imagine doing is you type a bunch of stuff, say you're typing your password in, and it'll just buffer all of that and send it all at once, as opposed to sending one stroke at a time or something like that. And that's one way of doing it, right? And then for timeliness, we're going to use the age of information metric, which is now 10 years old. Right, 10 years old. Yeah. It's a birthday party. So we're going to study this age leakage trade-off. Okay, great. So maximal leakage. Wait, is that? Yeah. Okay, so maximal leakage is, you can tell it's information theoretic because it has a log in it. Log means information theory. And it also has a conditional probability distribution, so therefore it's extra information theory. So what is it measuring? It's saying basically for every output, it's basically trying to find what is the most likely input, and then trying to measure sort of how much information is the most likely input, revealing about the output. One thing to note about this definition, much like differential privacy, it's only a function of the shaping mechanism. That is only, it is agnostic to what there's no distribution of X, so there's no assumptions about the distribution of the input traffic. So this is both good and bad. It's good because you get strong privacy guarantees, but it's bad because you can't then optimize over what your input traffic is going to look like. And it's studied, I say extensively, but it's studied a bit for continuous time processes. There's the age of information, which Roy should talk about because I'm going to say something wrong now. So the age at the monitor in our block diagram, the age at the monitor is the time difference since the last update was generated by the system. So since the last X was input was generated. And the idea here is that network effects like queuing will cause delays to the update sent by the monitor. So you want to control when you send something in order to control the age at the monitor. And I guess the initially counterintuitive thing to point out is that if you send a lot of updates, it'll just cause a lot of backup at the queue, and your actual the most recent ones, if you do first come first serve, will be sitting at the back of the queue, and you'll have a stale state at the server. And so the goal is to control then the expected age, and we're looking at it in this discrete time process, as opposed to a continuous time. So these two measures actually, if you look at them side by side, they actually seem kind of unrelated, because in AOI, what you're doing is you're fixing the network. You're saying, what if the network did this, behaves like this, behaves like a queue, for example, and then how do I optimize when I send information in order to control the age? Whereas in maximal leakage, you're saying the person is typing whatever they're going to type, and I'm going to control when I decide to send something. So what you get to control is actually different in both of the two models. So the question is, how do you combine these two perspectives? And then this is sort of the ongoing question that we're looking at. But we started out by looking at just fixing some policies, and then trying to understand what are the leakage age, what kind of leakage age trade-offs do you achieve by looking at these types of policies? So we looked at two types. One is kind of queuing policies. So like we look at a queue with an option to do some thinning of the input traffic. So we call this memoryless with Bernoulli thinning. And then we also look at another class of policies, which are accumulate and dump, which we call accumulate and dump, or which have been called by other people accumulate and dump, where you wait and then you wait for a time period, and then you just send the most recent packet that was the most recent update that was received. So like every 1 second, you will send something, whatever's been received in that last 1 second, the most recent thing that's been update that's been generated in that last 1 second. So the question is, what kind of trade-offs you can achieve, and because these are very cute, clean models, we can actually have formulas. So we have formulas. That's nice for theory, but we can also try and plot it. And it turns out that for example, the main thing is that any system that does any queuing is actually very costly in terms of age. So if we're privacy sensitive, queuing will make the monitor's information more stale. If we fix a certain leakage, privacy leakage that we want. But if we're latency sensitive and we want to fix, bound the expected age, then we have to leak a lot of information. So queuing is bad, maybe, compared to, which is worse trade-offs than sort of these accumulate and dump style strategies. So the ongoing and future work that we're trying to, what we did here is like focused on some very simple policies to get a feel for the trade-offs. And so then the natural question is, well, what is an optimal policy, or what is the best way to trade off these two things? And getting more and more speculative, and as we go along, like what if you can only partially design the policy? Because when you study age, you think of the network as not being something you can design. But here we're saying, but we can design. We're going to look at a particular queuing policy. So what if you can design how you're going? What if there's like two pieces of delay? Like one is controlled by you sending updates, and the other is the network. And then what does that mean about leakage? And then of course there's always this is a point-to-point system. You good for information theoretic studies, point-to-point systems. But then, once you start introducing multiple users or something like that, stuff gets a lot more complicated, but also a lot more interesting. So we're interested in thinking about that as well. So I think that's all I had. Right. So I guess the last point is that I think there's a lot of interesting open problems raised by communication systems and raised by timing and stuff that happens in the network that are like very different than the at least what I think of as traditional takes on privacy for machine learning. The first is that this idea is that that sensors in general and all sensing systems will collect data from multiple individuals. So if you have a room occupancy sensor, it's detecting events that are related to multiple people in the room, not just a single individual. So it's already doing some aggregation. And that the traffic is going to leak into these side channels exist, and that which way you think about privacy, differential privacy or maximum leakage, is going to matter in terms of what kind of guarantees you can make, obviously because of the semantics, but then also what kind of trade-offs you can achieve. You might have to weaken your privacy guarantee to get to be able to maintain some kind of reasonable QoS, for example. Okay, that's it.
All right, thank you.